Hello, welcome to my talk, Scratch Build Games by me, Andre van Houck, also known on the forums and GitHub as Treeform. Let's get into it. Why? Why do you want to build Scratch Build Games? Well, for me, primarily is to understand. I want to understand how games work, how low-level information moves around, and how to actually make them low-level. I also want to grow as a programmer. I think taking up something pretty challenging allows you to grow as well. And I'm a bit of a control freak. I want to know everything. Everything goes on. I want to have control over everything in my game, in my programs. So that's the reasons why I do it. In this talk, I'll talk about the lessons I've learned and the libraries I've produced from making games from scratch. Basically starting out from the most low level and going to a full game. We have a lot on the agenda today. I'll talk about all of these libraries, which is quite a lot that you would probably have to make something like this to make your own Scratch Build games. But the libraries are Windy for windowing, Steamworks for interfacing with Steam, my Pixie, which is a graphics CPU library, Boxy, which is a graphics GPU library, vmath, which is a vector math library, Bumpy, which is useful for intersections and collisions. Then we have Spacey, which is used for spatial partitioning. Then we have Neti, which is used for networking, JSON for JSON, Flatty for binary flat serialization, Zippy for zips and compression, and Super Snappy for even better compression. So yeah, we have a lot. Let's get into it. First, we have Windy, which you can find on github.com/treeform. Windy is a windowing and an OS API library. Basically, everything that deals with the low-level OS operations are part of Windy. First, making games, you probably want to target Windows, because on Windows, that's where most of the people are. They're mostly on Windows, and you probably want to target the Win32 APIs. Windows has a lot of newer APIs, but they are all built on top of Win32 anyways, and they're not as good, I would say. Win32 API has been with us for a long time. Contrary to its name, it's actually a 64-bit API. But yeah, there's two ways from Nim to interface with the Windows API. One way is to import the windows.h and make your objects and functions match the definitions in windows.h and match so that when Nim produces the C or C++ source code, it can just import WinH exactly as is and compile it out. It's actually pretty neat. The other way to interface with Win32 API is through what I call kernel 32 DLL, which is you interface directly with the binary API in the DLL. So first we went with windows.h, which is a text API. What you do is you specify a special pragma called header, and you do import CPP or import C to kind of look exactly how, so the type, once compiled to C, it will look exactly like the type in windows.h. So we tried this route, and we met a bunch of issues with it. First off, the Windows types don't make sense. The Windows H types don't make sense sometimes. They're kind of a little crazy. And then not only do you have to match whatever you generate to play nice with Windows H, you also have to make it nice to interface with like their binary API in kernel 32 DLL. So you can actually have the two things to keep in mind. We found it is much easier to interface with the binary API directly, which if you just interface with the binary API, you define the objects exactly how kernel 32 expects them, usually by looking at Windows H and similar files. You just look exactly at how it expects them to be, and then you just call the binary, like the C DLL API inside the DLL by using a dynamic lib directive instead. We had a lot more success with this method than with the text method when interfacing with the Windows API. I highly recommend doing that way. To see how we done it, just go ahead and look at the Windy repo. Next, interfacing with Mac OS. You want to interface with Coca. Again, there's like two ways, kind of similar. First, you have the Nim Objective-C way, where Nim actually has this almost hidden way that it can actually compile to Objective-C instead of just C. So, but then you kind of inherit all the Objective-C like ways as well. It's a little wonky. But it is doable. It is definitely doable. You can use that. Another way to do it is to interface with the lib Objective-C dilib directly. Guess which way we choose? Yeah, we chose the dilib, the binary API. We actually wrote this little cool macro that takes kind of like Nim definitions and converts them to Objective-C. If you know anything about Objective-C, you know that it has the most weirdest calling convention of all modern languages. It uses like weird message passing, which is kind of different from almost everything else. And like there is no function names. Like the names and the parameters are like the same. It's really wonky. But even Apple recognized this. So when they made their new language, Swift, they actually done away with that kind of crazy calling stuff, and they actually gave functions proper names, which is great. And this is the system that we use here as well. Basically the first parameter becomes like the function name. It's a little weird, but we basically, it kind of looks like Swift. So if you use Swift using this method with Nim, will kind of feel, well, maybe not the same, but at least similar. If you want to see how we done this Objective-C macro, go ahead and look at the source. It's pretty cool. Next, we have Linux. And this is the most I'm hesitant about. Probably will get a lot of flack for this one, but there's like many different ways to interface with Linux. So you have one way through the windowing system where you interface with X11 or Wayland, but it has drawbacks. First, Wayland, right? Not all the Linuxes have Wayland. Looks like all Linuxes that have Wayland have the X11 kind of like pass through or shim. I don't know. It's kind of weird. X11 is a really weird API. Wayland is newer, but it's like not ready everywhere. It's like the old stuff is deprecated and the new stuff isn't ready yet. That's how it feels like, right? The other problem with interfacing with window and system directly is that there are no open dialogues. So like, do you make your own? There's no notification, there's no train icons. Maybe not that important for games, for other software more so, but no IME, so no way to like input Korean, Chinese, Japanese characters into your game. That is kind of weird. Like IME needs to be there in order for people to communicate. Yeah, so that's weird. So then you can go a higher level up and interface directly with the desktop environment. And we also tried doing that. Yes, you get open dialogues, of the environment that you do. Yes, you get notification and you even get IME, but it feels big and heavy. Like the entire desk, now you depend on this huge thing. And the big problem is versions and updates. So it's like you'll probably bind to a specific version, but then they will update and then they'll break your stuff. And it is very common on Linux. Like the APIs, I wouldn't call them as stable. Not as stable as Win32, that's for sure. Yeah, and it's like in case of my game, I shipped my game. It runs fine to this day on Mac and Windows, but on Linux, some small version in the Pango has changed, so it like broke my game. And it's like, why are you making these changes? Like basically, if you ship a game to Linux, you'll probably have to recompile it, every couple years, even for the most popular, desktop distros. So it kind of pains me to say it. Maybe the proper API on Linux is actually Win32. Yeah, this sounds crazy. I don't want to say it, but it's practically, this is what it comes out to, especially for games, right? So Wine can play pretty much all Windows games. So if you write your game for Windows, it's highly chance that Wine will be able to run it. If you're going to ship your game on Steam, which I highly recommend you do, you'll probably run your game through Proton. It'll probably run fine. It'll probably run fine for years, because Wine and Proton is all about backward compatibility, unlike the previous APIs. So it's like, it's a little weird. Like, I don't want Linux to be this way. I want Linux to have like a single one good desktop API that like doesn't change after you ship your game, but it's just not true. Yeah, so you have to resort to some weird like this. Yeah, I know it pains me to say it, but that's like where I feel Linux is at the moment. Next, I want to talk about Steam and Steamworks. Again, you can find my library that interfaces with the Steam API on GitHub Treeform. I highly recommend shipping with Steam. So before Steam, I launched my game on my website. Yeah, I got some people, but it was very, very, very flat. Like, as soon as I put my game on Steam, tons of people tried it out. Yeah, it might not be true for all games, but for me, shipping it on Steam was my big break. I think without the discoverability, it is very hard to get your game out. Yeah, there's other platforms. I haven't tried them really, but I don't know. Versus shipping it yourself versus shipping it on Steam, it's no brainer. It's very easy to get your game up on Steam too. You pay them like $100 and your game goes in. Quite simple. Yeah, you basically want to be on Steam to follow the money. Again, there's two ways to interface with Steam, the Steamworks.h, and that's actually the first method I tried, and it was very difficult because Steamworks.h basically required you to use Visual C++ in order to interface with it. It's a C++ API, so it was like a little wonky to get it in, but I got it working. But then my game, like, it required to be compiled with Visual Studio C++, and I didn't want to use Visual Studio, and it worked fine on Mac. On Mac, I could use GCC, but on Windows, you had to use Visual Studio. It's like, all right, it was just very difficult. But after my learnings with interfaces with the Windows and Mac OS, I went back to this and interfaced with the Steamworks DLL directly. And boy, it was a lot easier. Like, yeah, everything just worked. Like, I think it took me an hour or two, whereas it took me days to do the other thing. Yeah, the binary APIs are just easier, and I didn't have to use Visual C++ for it anymore. I could just use, the normal thing, GCC or MingWi, like on Windows. So, yeah, pretty cool. So, try it out. If you ship your game on Steam, you probably want some small Steam integrations like accounts and DLCs and such. Next, I am excited to talk about another library, again, Pixie. It's a CPU graphics library. You can find it on github.com/treeform. Pretty cool. So this deals with CPU graphics. You probably heard of Pixie mainly regarding path operations. It can do fills, strokes, gradients, all that cool stuff. But really, it's not very useful for games. What you want for games is image processing. Mainly PNG loading, right? I highly recommend using the PNG format. I've used other formats in the past. PNG is by far the best widely supported formats. Yes, there are some specific formats for games like DDS, but if you're not making a 3D game, DDS doesn't really do much for you. I think for a 2D game, PNG is the way to go, even for assets that might makes sense more as JPEGs, but yeah, no, for games, if you're going to scale them or rotate them or do anything with them, PNG is definitely the way to go. Pixie has one of the fastest PNG reading and writing libraries, so yeah, you're in good hands here. You can easily take whatever you get from Pixie from the PNG and just throw it directly into the the GPU into a texture. So yeah, use Pixie's image capabilities to load the files. Next, you want to use Pixie for text. Yeah, text handling is not easy. It's actually quite hard to do. So when I first started, you could use a text atlas or something, but yeah, you quickly run into limitations, right? Like, what if you want to do Japanese or Chinese characters? Well, there's a lot of them. Like, what if you want to do different fonts? What if you want to scale it? Yes, there's weirdest ways to kind of get around that, but really, it's so easy with Pixie. Just to write some text into check texture and just upload it to the GPU. It's you could be writing all this code, but yeah, it's just easy. Like, Pixie just solves text handling for you. But if you're like me, you want to learn, you want to understand, go ahead and look how we did text. It's probably one of the simplest. Looking at other libraries is very hard. I think Pixie text handling is quite easy to follow, as easy as we can make it. But yeah, it's complicated. Yeah, text handling. So yeah, using Pixie for image loading and text handling, I would recommend you do that. Or, don't use the library directly. Go ahead and open up the lid and see how we done it, so you can learn and maybe make your own. There's actually some talks about Pixie from the previous NimConf and on my YouTube channel. So yeah, if you're interested in Pixie, go check it out. Next, I want to talk about Boxy, which is our GPU graphics library. As you saw, Pixie is all about the CPU. I believe operations that Pixie does is kind of low-level fiddly things like parsing formats or formatting text or parsing text. They're just better done on the CPU. Like there's almost nothing for the GPU to really optimize. But GPUs are really good at like putting pixels on screen, doing blurs and effects. So this is what Boxy is about. So first thing, Boxy abstracts all your OpenGL commands. Currently, Boxy is OpenGL only, mainly because I haven't gotten around to writing all the other backends. But yeah, if you're writing your own game, you need to have an abstraction between OpenGL calls and some sort of other graphics calls. But yeah, OpenGL Boxy just gives you a simple thing: load an image, put it on screen, you're done in like 3 lines of code. It's pretty cool. But that's not only what Boxy does. Next thing that Boxy does is the real-time atlas technology, which I think is really cool. So what Boxy allows you to do, this is primarily for 2D games, because let's face it, if you're making a scratch build game, making a scratch build 3D game is really hard. Like it's much easier to make a scratch build 2D game, and probably for people that want to make scratch build games, they're making 2D games. So 2D atlas here is like really good. So you can put images of any sizes, it will chunk it up in little bits, and it will stay very packed because of this. You can add and remove stuff in real time. Yeah, and it's pretty performant. I recommend doing something like this. So yeah, that's one of the big things that Boxy does for you is the atlas syntax. Next, it also does a bunch of effects like masking. Again, if you're making like an RTS games, you have a fog of war, or you have rooms and shadows that you don't want to see it. You know, masking is the way to do it, and Boxy fully supports this. Next, Boxy supports like shadows and blurs. You know, if you're like have effects, etc. Yeah, exactly. These are the kind of things that GPUs are really good at. Next, Boxy does blend modes. Which is again very useful for explosions, lighting, shadowing. Boxy supports pretty much all the blend modes you find in Photoshop. So yeah, you can actually do a lot with it. It's pretty cool. Again, just like with Pixie, you can find more Toxie on YouTube. Just search Treeform or my name, Andre Van Houck on YouTube, and you'll find the Boxy talks. Yeah, pretty cool. Next, I want to talk about vmath, which you can find again on github.com/treeform. It's my vector math library. I actually recommend everyone who wants to build scratch build games to make their own vector math library to learn, maybe not to use long term, maybe like Pixie, vmath just does everything for you, so just use that. But to learn, I highly recommend doing at least like a poor man's version of a vector math library to understand how vectors work. I did not understand how vectors work before I written my own, so I think it's like a rite of passage for any scratch builder to make their own vector math library. Maybe not to use long term, but at least to make once. So yep, vmath supports vectors. They support most vector operations, and they're mostly in the GLSL naming convention. So if you have used GLSL, which probably you have if you've made games before, it should come naturally to you. Many algorithms for vectors are written in this method. Yeah. So yeah, GLSL, like all the swizzling operations are there. Yeah, just it's easy to transition to because it's very familiar to everything else. It also supports matrices and many of the matrices operations that actually GLSL does not support, but we had a bunch of those as well. You can do almost anything you want with matrices with vmath. It supports all that. It even supports quaternions. Again, you probably aren't using quaternions for a 2D game, but if you're making a 3D game, quaternions are a must for motion and animations. Yeah, it supports them all as well. If you want to learn how to do the quaternion operations, again, just go look at the source code. vmath is pretty approachable. Yeah, pretty cool. So yeah, use vmath if you need to. Pretty much all my libraries at the low level depend on vmath. Next, I want to talk about Bumpy, which again you can find on github.com/treeform, which is intersection testing. So at first I was thinking of using like a 2D physics engine for my games, but the physics is just too real. Something that I found with making games is you actually don't want real physics. You want like fake physics. You want to like fake it and make it more fun. So here, Bumpy supports almost all of the operations that you want. You know, it basically supports intersections between all of these primitives, you know, point to polygon, segment to polygon, rectangle to segment, circle to polygon, etc. Like all of them supported. There's a bunch of collision primitives. Most games will only use like 1 or 2 collision primitives. So if you don't want to include the whole library, just look at how I done it in the code. For your, you know, maybe like polygon to circle is all you need. Like polygon to circle and circle to circle. Probably like 99 of the games can just be done with those collisions, but sometimes it's useful. You have you know, line, for instance, when you're shooting a bullet, or you know, you just want to see if a point is inside somewhere. So yeah, all that is there. Go ahead and take a look, or import the library and just use it as is. Yeah. It, I think, is important to do your own collisions, because yeah, if you're writing a very like physicsy game, maybe, but it's usually a gimmick. If you're making a 2D game, you want the collisions to kind of be not real, but be fun instead. So this is what allows you to do. I don't know what fun is for your game. You have to figure that out. But I do provide you the collision and the intersection stuff, so you can find all the points that have collided and do stuff with that. Pretty cool. This is especially true in like a 2D platformer. Feeling good is extremely important. Like 2D platformers don't follow real physics at all. The jump mechanics are like really interesting. The double jump, the air jump, like yeah, there's a whole art to how to make basically like physics not real and fun. Yeah, and Bumpy allows you to do that. For my game, which is more of an RTS spaceship shooter type of thing, you want to predict where the spaceships go. They have weapon arcs. Again, Bumpy excels at that. So yeah, it's all there. You want to make the simulation fun, not realistic. Next, I want to talk about Spacey, which again, you can find in my GitHub, and it does spatial partitioning. This is very important for games. As you start adding more and more enemies or more things in your game, it will basically become slower and slower and slower and slower, because you're probably just using for loops for intersections or collisions or other AI logic. What you actually want is spatial partitioning. So for instance, in this example, you have like a red, which maybe represents like your character, and then you only want to interact with people that are interactable, like in your circle, in your like sphere of influence. And this is what spatial algorithms do. You don't need to think about everyone outside the circle, it just gives you the stuff inside the circle. The way I wrote Spacey is it's actually very modular. If you implement the Spacey API, you can basically switch different spatial algorithms. This is what I've learned through my days of doing this, is that there's no one that fits all. Like all of them have like drawbacks and benefits. So yeah, let's get into it. Like basically what I would recommend you to do, either use Spacey or make your own Spacey. Pick, you know, make the API be similar, and then for any use case, cycle through different implementations and see if they're somehow faster or better or more useful for you. First one, what I call is brute space, which is actually just a for loop. So if you were using for loop in your game before, you can quickly convert to this for loop. It uses the power of small numbers. So the more complicated spatial algorithms actually don't do good if you have like less than 10 things on screen. So if you have less than 10 things, actually brute space is faster, because doing a for loop over 10 things is faster than creating a complicated data structure that might basically eventually will do a for loop over those things. So yeah, so sometimes brute space actually wins. It's some small numbers it does. Next, I have the sort space, which basically uses the power of quick sort to sort everything on one axis, and then you just basically look to the right or to the left of you. So this is really useful. I actually use this in my game for collisions between ships. So in RTS game, when you select a bunch of units and they move in clumps, this is actually pretty good. And everything else that clumps up, like I don't know, like ball pit or something, like this is actually like better than the other spatial algorithms, surprisingly, because you can kind of stop. You can kind of like, oh, I've done enough collisions, and you know, if you like if you have a bunch of like nodes tight, a bunch of units tight in a clump together, like you actually don't care that it's like going to collide the one like 3 over. No, you just care about collisions like 1, 2, or 3. That's it. That actually keeps your simulation from exploding as well. When everything gets really tight, it has like a notion of like just like flinging everything into various directions. Not fun, maybe more realistic, but not fun at all. So yeah, this kind of sort space kind of keeps it, you know, neat that way. So yeah, if you have a bunch of tight objects all packed together and you just want to care about to like to the right, to the left, or something of you, sort spaces is the way to go. Next, I have hash spaces. So this uses the power of hash tables. What it does is it basically every position goes in a tile. There could be infinite number of tiles. You don't have to like have an array of tiles by tiles. Hash space just kind of like naturally scale. This is really useful because you can tweak the size of the tiles to your game, and this is what I found. If your tiles are like off, yeah, this will be slow. But if you like, in my game, for instance, I have a maximum size a unit can shoot, and my tiles are basically based on like max interaction distance. So if you make those tiles, it actually does speed up and can be faster than the next algorithms that I'll talk about. So yeah, hash tables are easy to understand, easy on the processor. There's not that many allocations that happen. Yeah, highly recommend. Try out hash spaces and see if they're the best one for your scenario. Next, I have quad trees. I call them the quad space here. It uses the power of subdivisions. Basically, when there's a lot of stuff in a node, it subdivides it further. Yeah, this is, when you talk about spatial algorithms, I think this is the one that comes up naturally. Pretty much everyone just says recommend to this. And yeah, it's pretty good. Yeah, if you just import Bumpy and you don't want to think about optimizing stuff, yeah, just use a quad space. It'll probably be good enough for your use case. Pretty much good enough for all use cases. But again, you know, maybe the hash table is actually faster in your use case if you dial the tiles correctly. Yeah, so yeah, quad spaces, yeah, really good. But there's actually another algorithm that's like even better, I think, for some things, called the KD space. It does the same idea, it subdivides the nodes, but it actually doesn't make them equal size. KD spaces are actually slower to build than the quad trees. I recommend using this for static assets. You just build them once, and then yeah, you never have to update or redo it again. And it's actually slightly faster than the quad trees for a lot of things. So yeah, KD spaces. So again, the biggest thing, the biggest takeaway, or the biggest my learning of this is that there isn't a spatial algorithm that just like fits all cases. You can actually mix and match them to get the best performance. And yeah, this is what I learned. If you have very few elements, brute space is the way to go. If you have like almost like a molecular simulation type of ball pit type of situation, yeah, use sort spaces. They're probably the way to go. Quad trees, you know, pretty good for everything else. You can really fine tune the hash spaces, and KD stuff for static stuff just makes a lot of sense. Next, I want to talk about Slappy. Again, you can find that on my GitHub. It's my sound library. So we've done almost everything. We've done the windowing stuff, we've done the math stuff, we've done the graphics stuff, we've even kind of touched a little bit on the AI/spatial partitioning stuff. Next, we have sound, right? So first off, you want to be able to load the most common format there is, the WAV format. It is a very basic format, but it creates very large files. In fact, the format is so basic. Go ahead and go look at the code. It's like 10 lines of code to load a WAV file. It is laughably small. Yeah, and almost all tools support it. It is really cool. Yeah. If you have a game, I highly recommend using the uncompressed audio for sound effects. If you use compressed stuff, you might actually start here like over time. Doesn't sound as good, but yeah, uncompressed is always just going to be better. Especially if the player has to hear it over and over and over again. Yeah, use waves. Use basically a lossless format. But I have a different format, the OGG or OGG, right? It's a compression format, but it's lossless. Yes, you probably seen like MP3 or other like sound formats that are probably more popular, but MP3 specifically has like patent and stuff, and it's kind of weird. OGG is a very good open source file format. It is supported for pretty much all sound apps. So for music, or like background effects like wind or something, yeah, you should use this file format. It produces lesser files, all tools supported. It is more complicated to load, so if you want to learn how to load the OGG, yeah, go look at the source code. But yeah, I don't you know, don't implement yourself. It's a little hectic. Yeah, just use it. Yes, that's good. Next, Spatial positioning. This matters less for a 2D game and, you know, scratch build games. It's probably a 2D game that you're building. But here I use OpenAL. I actually kind of like upset about this. I want to write my own positioning system in the future. Basically rewrite OpenAL my way. But for now I'm using OpenAL, and that's actually good enough. Like, it does everything for you. You know, you move your guy around the screen, different sound sources, they get louder or less louder. They go off screen, they get less loud. The bullets have the Doppler effect. Yeah, all that stuff is built into OpenAL. It's actually pretty easy to use. It's all wrapped for you here in the library. Yeah, try it out. There's other tools like fmod and stuff, but yeah, OpenAL just does it all for me for now. Yep, go ahead and take a look. Next, I want to talk about networking, specifically my Neti library. Again, you can find that on my GitHub. My idea with Neti, I've used TCP for games before, and I tried using UDP for games, and I just want the reliability of TCP, but TCP is not designed for games. Like, the hacking is weird, like a bunch of stuff is designed for like throughput. So what I did is I basically made, you know, what I want UDP to be. I want UDP to be lossless and like reliable, and I want it to be used for games. And this is basically what I made. It's basically, you know, Neti is just basically a reliable UDP. And here's how I come. If you want to build your own reliable UDP, here's how you would do it. First, you gotta think about the resends. Like UDP packets, if you're sending UDP packets, they'll get dropped eventually sometimes, and you need to send them back. What I use in Neti is extremely aggressive resends, right? If I don't receive an ACK like right away, I'll send you resends. Much longer than TCP would. Yeah, and this is basically what allows kind of more snappier nature. Because yeah, if you miss the packet, like, you get it right away. Yeah, and you have to resend it basically in order to get, you know, packets in order. Next, you have to talk about the order. UDP packets usually arrive out of order, so you kind of want to reorder them as you go. So this is what Neti provides. They come in out of order. I make them in order. Everything's good to go. Next thing with UDP packets is actually like kind of like a max size, but it's really fuzzy. Basically, the larger you make your UDP packet, the higher chance it is of getting either dropped or not through completely. Like, different networking equipment seems to have like different sizes that they support. So what I do is I basically pick the size that works everywhere. And what I do is you send a large Neti packet, but I will break it up in a bunch of little UDP packets, and then I'll stitch them back together on the receiving end. Yeah, so this packet like is really important, because sometimes you do want to send like larger things, and they will basically just never arrive. So you have to break it up, and like, yeah, Neti, the layer, just does that for you. And if you were writing a reliable UDP wrapper, this is the stuff you would have to do. Another cool thing that Neti provides you is UDP hole punching. This is something that TCP cannot do, but UDP can. So it's a little complicated to get going. You still have to have a central server that everyone can access, probably like a high scores, or maybe like a game server where the people can like find games and find each other. You need to have some sort of like a matchmaking, like a, you know, server. After the two clients, yeah, clients currently, pretty much all players sit behind a firewall. Firewalls are very common, pretty much all routers have them. You very rarely have a player that doesn't have a firewall around them. So what you want to do is you want to have two players communicating with each other without your central server getting involved. This basically saves you from having the central server. It saves you from you know, bandwidth costs, etc. Right? Yeah. So yeah, if you only have like a little matchmaking server, just makes matches, and then the clients basically talk to each other. It's pretty cool. But yeah, they're behind the firewall and they can't talk to each other. So you do this hole punching. Is they talk to central matchmaking, and then it basically tells one client, hey, talk to that one, and then takes to that one and says, hey, talk to this one, and then you basically punch through the firewall, and then they can start talking to each other. It's pretty reliable. It's pretty cool. It works. It's great. And so Neti has the support for it. But yeah, you write the central server yourself though. Yep. Another thing that Neti has is no async. So UDP does not block by default, so why would Neti block? So it is much more natural in games to operate on ticks. So you get your ticks, you look at your keyboard input, you look at your mouse input and joystick, whatever, and you look at your network input and the same like stuff. And then maybe you have to draw a frame. Yeah, working in ticks for a game environment is just much easier than doing some sort of async stuff, because again, you're not streaming stuff, you're not, it's a packet-based system. So yeah, it's much easier to work in packets, I feel like. So yeah, Neti has no async, so your game doesn't need to do async. Neti does have drawbacks, and using UDP like this does have drawbacks. So if you're sending lots of data, it's probably not a good idea to use, like if you're transferring big files or you're loading assets over network, yeah, probably use TCP for that, really, or even HTTP, just download them from like a CDN. That would be much better. There's also no real tooling for Neti, like Wireshark doesn't understand Neti, right? Yeah, so that's the drawbacks. Next, I want to talk about JSON, which is JSON serialization and deserialization. What are you going to put in those packets? You got to put some sort of data. So I recommend maybe to start out of, just send JSON. JSON is one of the fastest JSON serializers. So yeah, just put your packets into JSON. You can just send them with Neti really easily. It's really easy to debug because you see exactly what's in the packet. You can interface with not Nim stuff. For instance, maybe your server is written in a different language, like maybe Node.js or something, or maybe your client is written in a different language, like if you're using Unity with C#. So yeah, communicating with JSON is easy. It's interoperable. So yeah, I would recommend that for that. But I think binary serialization is better for your own game. So, and this is where I have Flatty. Again, you can find it on my GitHub/treeform. But it's actually, those things are really fun to write. I highly recommend writing binary serialization. It's just cool. I enjoy it. So, or if you don't want to use Flatty, fast binary serialization is like 10 times faster than JSON, and JSON is already pretty fast. So yeah, it's pretty cool. It produces smaller packets, smaller things. Unfortunately, it's NIM to NIM only, because what it does is it packs NIM's data structures directly. For speed, it just does a copy mem, so it's like really cool. But yeah, interfacing into a non-NIM language will be much harder. So yeah, if you do both, you're like, both ends of the pipe are in NIM, Flatty is the way to go. It is slightly harder to debug. Again, it's not text, so you can't view it. It can also be a little fragile in case that, if you modify your code, it'll also modify like the format of the packet, so you have to be mindful of that. Basically, if your two clients talk to each other, you have to make sure that they're backward compatible yourself, or basically say no, if you have different versions of clients, they can't talk to each other, which what most games do. So like for my game, yeah, if you're different versions, yeah, you just can't play together. It's very normal. I think it's very usual for games. Yeah, nothing to be afraid of. So yeah, this is where the serialization is. If you want your stuff to be backward compatible, maybe JSON or something like Thrift or something is better. Next, I want to talk about Zippy, which is actually not by me, by Guzba. He did a really good job here. So Zippy does everything around like what zlib does, but in pure NIM. So it does compression and also does archives such as zip files and tar files. It's pretty cool. I recommend to use zip files for your game assets. Like that's just I found works the best. So it's very easy to debug because you can easily just uncompress and see what's inside. It's very easy to interop with other tools, like if you're making assets, say in Python or maybe like Bash, you just zip them together. Yeah, it's very easy to make asset zips. Yeah, and Zippy supports them all, so it's like really easy, really cool. Not a problem at all. You could also use the kind of the compression of Zippy to kind of sense packets. So your network packets could get kind of large, so you could kind of compress them while you send them. It's pretty cool. But I think for stuff like network packets, a better idea is actually super snappy. Again, written by Guzba. You can find it on his GitHub. It's really cool. I think snappy, the algorithms, stands somewhere in the middle, or like at the apex of being pretty simple. Unlike zlib, which is like a very complicated algorithm. It's pretty simple. It works on byte level, means it's really good on modern CPUs, unlike the binary streams from zlib, right? It works on bits, so it's actually kind of slower. It doesn't fit the modern ZPUs, while Super Snappy does. And the other thing with Super Snappy is it's just you know, it's in pure nim, so it's like, you know, really easy to use. Yeah, it's just like in this apex of being small. Oh, it produces pretty good compression. And it's not the best compression. You could probably get better with other stuff, but it's like good enough for most things, to be honest, right? It's like, yeah, so it's like, it's pretty small. It's pretty good for current CPUs, and it produces pretty good compression. Highly recommended. It is faster than using zip or zlib. I highly recommend use it for network packets and for internal assets. Actually, when I talked about Wave before with Slappy, I kind of lied. I have my own file format for sounds, which is basically kind of like WAV files, but compressed with Super Snappy, right? And I basically create a bunch of little file formats for my games, you know, to store like levels in my games or character animations. Yeah, I just store them in as sometimes as zip files and just compress them with Super Snappy. It's like a really good file format, just like, you know, sprinkle little compression, you know, on almost everything you make. It's pretty cool. So that's what I actually use for my games, is these little file formats that are basically based on Super Snappy. I highly recommend. It's really cool. The Goosebumps Super Snappy implementation is blazingly fast. It is even faster than the reference implementation done by Google. So yeah, it's pretty cool. Yeah, so that's basically leads me to the end of the talk. It might have sounded a little bit like a sales speech, but like in order to make a scratch build game, you have to make these libraries or get them from somewhere else. Like what I like to do in the past is basically look at a library and say, oh, you know, this library is pretty small enough, like a header library. I love header libraries, right? So I try to write my libraries in the same way, kind of, yeah, they're not really together that much, right? Maybe vmath is used in a lot of them because it's just like basic stuff. But like, yeah, you can mix and match, pick and choose, right? Like, yeah, there's some parts, maybe you start out with my library and then write it from scratch. Maybe you start out with my library and like look at how I did it, and then you say, oh, you know, I want to do it differently, or like specifically for my use case. No problem. Maybe you never use my library, but just look at the code or just like to learn from. Yeah, just use the parts you need for your scratch your games. That's what I did, and that's what I recommend other people do. And keep rewriting stuff. I think while you rewrite something, you do learn something, you do understand something. I think it's important. That's basically it. Thank you for coming to my talk. Yeah, it's been great. See you around on the NIM forums or the Discord or IRC. Bye.